Here we're modeling volume as a function of the radius of a balloon. So if you can imagine a balloon, the radius is basically from the center of the balloon to any one of the sides. That's the total radius. And the amount of space that can fill up the balloon is the volume. So volume is calculated this way for a sphere. Balloon will pop when the radius is approximately 25 centimeters. So we want to know that the amount of helium needed, the amount of volume that will be taken up by using up different for different radius of the balloon. So if we do this for 12, that means we need to do 4/3. So in parentheses, I'll do 4 divided by 3 times pi, second the caret button, the exponent button, and then now we can put in our radius. So if it's 12, we'll put in 12, raise it to the third power, and that tells us the amount of volume needed for a 12 centimeter balloon. Now we do this the same thing. Now if you hit second enter, that will pull up your last entry, and now all you need to do is change your 12 to your 14. And you can continue going this way. So one trend that we'll notice is that as you increase the radius, the amount of helium needed also increases. So the dependent variable and the independent variable, well, that's the equivalent to saying output and input. And the input in this case, well, a volume is the output, and input is the radius, because it's volume is a function of that. What would be a practical domain and range for this function? So a practical domain would be, well, it says that the balloon is going to pop at 25 centimeters, so we have to have less than a radius that's less than 25, but on this side we can't have a radius of 0 because that doesn't form a balloon, so we know that it can't be equal to 0, but it can be anything bigger than 0. So that means, well, if you have a on this end, anything greater than 0 for a radius, well, that will produce a volume that is also greater than 0. And, well, what's the biggest volume we'll have? Well, it's going to be less than the volume corresponding to a 25 centimeter balloon. So what I'll do is I'll come in here and I'll just try to see what the volume is for 25 centimeters, and I find out that it's 65,449, we'll just round to one decimal place, 0.8 cubic centimeters. How much helium would you need to fill 100 balloons if each has a radius of 15 centimeters? Well, if each has a radius of 15 centimeters, that means that each one would have to have a volume of 14,137. So that's how much helium you'd need for one balloon. But we're going to multiply that by 100 since we're talking about 100 balloons. And here is the number that we come up with. So in I don't know how I labeled these. So this should actually be C, and this should actually be D, and this is E. No, I'm sorry, these are both parts of C, and this is part D. And part D says how much volume would you need, and we calculated that to be 1413716 point about 7. So about that many cubic centimeters. In part E, we want to rewrite the volume formula using function notation. Use R to represent the input and H of R to represent the output. So the amount of helium as a function of the radius of the balloon is equal to, the way we calculate it, by taking 4/3 times pi times the radius to the third power. That will give us the amount of helium. F, is the graph increasing, decreasing, or constant? Well, without even graphing this thing, we should be able to say that it's increasing. In other words, if you look at input, which is the radius, and you look at output, which is the volume, we should expect that as you increase the radius, the volume should go up as well, and we're seeing that in the table. In part G, how can you determine just by looking at the graph that it is a function? Well, a function, remember, means for every R, every radius, there's only one volume. Well, is that true? Well, certainly you could argue that you couldn't argue that a balloon, that if it has a certain radius, will have more than one volume. Every radius corresponds to only one possible volume for the balloon that we're talking about, as long as all the balloons are the same.